Alright, so today we're going to talk about graphs of rational equations, and our goal is to be able to graph a rational equation. And a rational equation is an equation that has a polynomial in the numerator and the denominator. And we're going to do that using some key values as well as some t-tables. And so when we look at a rational function, if we just call it v of x, alright, so usually it's f of x or something like that, but if we just call it v of x equals p of x, so some other polynomial, divided by some different polynomial. So p of x divided by d of x. So p of x and d of x are polynomials. What do we mean by that? We mean that p of x could be something like x squared plus 2x over d of x could be 3x minus 7. Those are both polynomials. So where p of x and d of x are polynomials, and d of x cannot equal 0. Why can d of x not equal 0? Because we never ever want to see a fraction where we end up with 0 in the denominator. This is a no, no, no. Alright? The domain of that polynomial then, the domain of v of x, would be all real numbers except, alright, so except the zeros of d of x. In other words, the values of x that make d of x equal to 0. Alright? So, if I'm looking at something simple, I'm going to go back into my equation here. I'll erase the 3. If I said, what value can you not plug into this polynomial up here? Obviously, hopefully, you said x cannot equal 7, because that would make my denominator 0. Okay? So we're going to start off with something called the reciprocal function. And this function is f of x equals 1 over x, and we're just going to fill in some values for f of x below in the t-table. You'll notice the first one is 0. If you plug in 0, you get 1 over 0. You can't have that, so 0 is undefined. Not sure why I did it twice here, but it would also be undefined on the right side as well. If I plug in 1/5, now this is where this is going to get a little bit tricky. So if I plug in 1 over 1/5, I'm going to have to do a little flip and multiply with that, so that becomes 1 times 5 over 1, so that's going to give me 5. The same thing is going to happen if I plug in 1/3. Imagine just changing the 5 to a 3, and it becomes 1 times 3, and so I get 3. If you plug in 1, you get 1 over 1, that's 1. If you plug in 4, you get 1 over 4, that's 1/4. If you plug in 5, you get 1/5. If you plug in 10, you get 1/10. You plug in 100, you get 1 over 100. You plug in 1,000, you get 1 over 1,000. Alright? So, the right side, if we do negative numbers, all it does is change these guys on the left to negatives on the right. So if I divide by negative 1/5, it's going to be negative 5. If I divide by negative, now this time I chose negative 1/4 for some reason, not sure why again, but that's okay. If I plug in negative 1/4, just think about it, 1 over negative 1/4, I'm going to flip and multiply, so that becomes 1 times 4 over negative 1, and that's just negative 4. So my next one would be negative 3, 1 over negative 1 is negative 1, 1 over negative 5 is negative 1/5, and then negative 1/10, negative 1/100th, and negative 1 over 1,000. Okay? So I'm just going to graph a few of these, and we'll take a look at them. The first thing we want to do is we want to look at this undefined piece here. When x is 0 anywhere along the vertical y-axis right here. Okay, x is 0 all up and down here. But because I'm undefined, what I'm saying is my graph can never ever touch that, and so I'm going to draw what we call a vertical asymptote up and down the y-axis here. And that vertical asymptote is a place where x can never ever touch. Alright, so let's take a look at our table. I'm not going to graph all of these obviously, but I'm going to try and graph some of them. So I'm going to start with 1/3, 3, because 1/5 I'm going to have a really hard time with. So 1/3, 3 would end up right about here. 1, 1 is going to end up here. 4 comma 1/4 is going to end up here, and you see real quick that if I try and keep going, 5 comma 1/5, I'm even lower. So it gets really hard to graph, but you know, if you look at the table, these are all numbers that are bigger than 0. A fifth is bigger than 0, a tenth is bigger than 0, a hundredth is bigger. These are all bigger than 0. If I continue to plug in bigger and bigger numbers, they're all going to be bigger than 0, but they're all going to get closer to 0. So as my graph comes in, it comes against the vertical asymptote, and it's just going to continue to hover right above the x-axis, because even if I plug in 1 billion, I get 1 over 1 billion, which is still greater than 0. And the same thing happens on the negative side. Negative 1/5, negative 5. I can't even hardly graph that. Negative 1/3, negative 3. And again, I'm not graphing them all. Negative 1, negative 1. Negative 5, negative 1/5. And you can see, even at negative 10, I'm still just barely underneath the x-axis this time, because again, no matter what I plug in from the negative side, I am going to end up with a number that's just below 0. When I say just below, I mean something that's negative. And so what happens here is we actually end up with a horizontal asymptote here. So this line here, or your x-axis, becomes your horizontal asymptote, and that horizontal asymptote is y equals 0, and your vertical asymptote is x equals 0. The vertical asymptote is easy to find because it's the value where x is undefined. So I'm going to call this vertical asymptote x equals 0. How do I know that? I can see it in my t-table right here. All right, anytime I end up with 0 in the bottom, whatever that number that made the bottom 0, that becomes your vertical asymptote. All right, so here we go. Let's take a look. The next section talks about end behavior. Okay, it says, in words, describe the end behavior of f of x. Well, what do they mean by that? Basically, what they're saying here is they're saying as x gets bigger and bigger, when we say end behavior, we're saying as x gets bigger and bigger, all right, as x gets bigger and bigger, they're asking the question, what happens to y? So that's the right side of my graph. And you can see that as x goes this direction to the right, my y values come down and get closer and closer to the y-axis, or in other words, the y values are getting closer and closer to 0. And you can see that in the t-table. As I move down the t-table, as my x values get bigger on the left, on the right side here, my y values are getting smaller and smaller. So as x gets bigger and bigger, y gets closer to 0. And likewise, we could say what happens on the other side of the table. All right? So if you look at the other table, all right, x is getting smaller on the right-hand table. We go all the way from negative 1 to negative 5 to negative 10. So x is getting smaller, and my y values on the right side of this table are also getting closer and closer to 0. So we could say as x gets smaller and smaller, okay, so I just want you to realize as x continues to get small, all right, y gets closer to 0. But it doesn't ever touch 0. Because no matter what you put in the bottom of the function, remember our function was f of x equals 1 over x. So no matter what number I put in the bottom of there, as long as it's not 0, I'm going to get a number. And the bigger x gets, the smaller this fraction gets. Or I should say, the closer it gets to 0, not necessarily the smaller. All right? So if you go down here just a little bit further, notice the notation. So I gave it to you in words the first time. This time I'm going to give it to you in notation. So we said as x gets bigger and bigger, y gets closer to 0. So we take this, and in notation we say it like this, because we don't want to write this out every time. That's too much to write out. We say as x goes to positive infinity. That's what this little arrow means. As x goes to positive infinity. What does that mean? It means as x gets bigger and bigger, y goes to 0. Y gets closer and closer to 0. As x gets bigger and bigger, y gets closer to 0. And the same thing happens with x moving to negative infinity too. That's this second one right here. As x goes to negative infinity, as x gets smaller and smaller, y goes to or gets closer to 0. All right, so that notation is something that you're going to want to be familiar with as we go through this unit here and the graphing. So what does this tell us about the end behavior? What this indicates is that the end behavior indicates that the graph of f of x equals 1 over x approaches but does not cross the x-axis. So as you saw up above, that graph got really close to the x-axis from the top and from the bottom, but it didn't cross. Therefore, we say that the line y equals 0 is an asymptote. Asymptote for the graph. More specifically, we would say y equals 0 is a horizontal asymptote. How do I know that it's horizontal? Because it's y equals 0, not x equals 0. Okay? All right, so our next one is to take a look at a similar looking function, but this time it's 1 over x squared. Not just 1 over x, but 1 over x squared. So again, we'll go through the t-tables. We're not going to make them as big this time, but if I try and plug in 0, I get 1 over 0 squared. That's still undefined, guys. Anytime you end up with 0 in the bottom, it's undefined. All right? So right away, when I see 1 over 0 or any number over 0, not 0 over 0, we'll talk about that later, but if I see any number over 0, this implies that there is a vertical asymptote. All right? Any number over 0 that's not 0, so negative 3, negative 4, positive 10 over 0 implies vertical asymptote. So as soon as I plug in 0 and I get undefined, I know that this is vertical asymptote. X equals 0. So I'm going to go and graph that right now. Straight line. We usually do asymptotes as dashed lines. If you were to do this on a graphing calculator, they don't actually graph the asymptotes. They're not physically part of the graph. All right, so we got some fractions to pop in here again. This ought to be fun. We got negative 1/5 and we have to square it. So let's see what we got here. So if I plug in 1 over negative 1/5 to the second power, that becomes 1 over, this is going to be, if you square negative 1/5, number 1, it becomes positive. Number 2, you square the 1, that's 1. You square the 5, that's 25. And then you still got to do all your flipping and multiplying, so this becomes 1 times 25, which is 25. You do the same thing with a 4th, and you get 1 over 16. You flip and multiply, you get 1 times 16, this is 16. Same thing with a 3rd. You square it, it becomes a 9th. You flip it over, this becomes 9. Now, we get to negative 1. We do 1 over negative 1 squared. Well, negative 1 squared is still positive 1, and 1 over 1 is still 1. 1 over negative 5 squared. Well, negative 5 times negative 5 is 25, so this becomes 1/25. And then 1 over negative 100 squared becomes 1 over 10 10,000. All right? And it doesn't matter if they're positive or negative here, because anytime you square something, it turns out to be positive. So whether I plug in negative 1/5 or positive 1/5, I'm going to get 25. If I plug in negative 1/3 or positive 1/3, I get 9. I plug in 1, I get 1. I plug in 4, I get a 16th. I plug in 5, I get 1/25. I plug in 100, I get 1 over 10,000. All right? Let's graph some of these guys, see what we got. All right, let me see. I can graph negative 1/3, positive 9. I can barely get that one on there right at the top. I can graph negative 1, 1. I can graph negative 5, barely graph negative 5, 1/25. You'll notice all of these numbers on the left T-table here are still bigger than 0. Even 1 over 10,000 is just a hair above 0. So I have a curve that comes down against the vertical asymptote, goes out towards negative infinity, but continues to hover just like the previous graph, except now instead of being below, it's up on top. Same thing on the right side. All right, 1/3, positive 9 would end up somewhere about there. 1, 1, 4, 1/16, 5, 1/25. And you can see that this graph is literally imitating itself across the y-axis. It's just reflected from one side to the other. And again, the reason it's doing that is because of this squared down in the bottom. Okay? So, describing the end behavior of this graph. Okay? Again, I'm going to give it to you in two ways, but quickly we're going to transition into just the notation. So we'll start off the same way as last time. As x gets bigger. Okay? We don't need to say bigger and bigger. As x gets bigger, y gets closer to 0. How do I know that? Look at the T-table again. The x's, the right-hand T-table, the x's going down the column are getting bigger and bigger, and the y's going down the right-hand side are getting closer and closer to 0. As I go down the T-table, they get closer and closer to 0. All right? So in notation, I would say, again, as x, and I'm going to bring this down purposefully, this is how the notation goes. As x moves toward or goes to positive infinity, y goes to or gets closer to 0. So that little arrow basically means it's going in that direction. All right? Doing the other side, as x gets smaller, y gets closer to 0. So this guy, the notation goes like this. As x goes toward negative infinity, y goes toward or gets closer to 0. Okay? So the end behavior indicates that the graph of g of x equals 1 over x squared approaches again, but does not cross the y-axis. Neither one of these graphs crosses the y-axis. Therefore, again, we would say that the line y equals 0 is an asymptote. A-S-Y-M-P, tote. And specifically because it's y equals, it's a horizontal asymptote. Giving the domain and range of g of x, well, let's go back and take a look at the graph here. My graph, if you look at it, it goes all the way to the left because of that arrow, so we're talking domain. It goes all the way to the right because of the red arrow on the right side. But as I come across the graph this direction from negative infinity, I get to this asymptote and I literally have to go jump to the other side and then continue towards positive infinity. So I am never going to touch the value of x equals 0. So my domain is x in the set of reals such that, or where, x is not equal to 0. Take a look at the range. My graph never goes below the x-axis. It's always above the x-axis. So this graph never even touches 0 at the bottom end, but then it goes up forever and ever. So we could say that the range is 0 to infinity, not touching infinity, parenthesis, not touching 0, parenthesis. Okay, so as we finish up this lesson here, we're just going to talk about a couple of ways, things that will help us out in graphing here. So we're talking about horizontal asymptotes again. The line y equals k, all right, so k is some number. It could be a fraction, it can be a whole number, it can be a decimal, it could be positive, it could be negative. So the line y equals k is a horizontal asymptote of a function, and we just named our function v of x. It could be f of x or whatever. Is a horizontal asymptote if, as x goes to negative infinity, y goes to k, or if, as x goes to positive infinity, y goes to k. So in other words, as my graph, if I were to draw a graph here, and I had a graph that looks something like this, all right? So it might be doing something really funky here. So let's just say I had this asymptote, and we're just going to call this y equals 3. So I could have a graph that's coming, you know, something like this. How would I do this? Believe me, it can be totally funky. So maybe it just looks like this. Maybe it comes up and rolls around, boom, like that. And maybe there's a vertical asymptote over here. And then maybe there's another part of the graph up here like this. So as x goes to negative infinity, my graph is going closer and closer to 3. As x goes to positive infinity on the right side, my graph is getting closer and closer to 3 from underneath. Okay? Those are horizontal asymptotes. Vertical asymptotes, the line y equals h. Okay? So we'll just say that this is maybe, this should actually be x equals, pardon me. The line x equals h, all right? So again, x can be any number here, so let's just call this x equals negative 2, all right? So the line x equals h is a vertical asymptote for the function if, as x goes to h from the positive side, you see this little plus sign up here? That means as x gets closer to negative 2 from the right side, from the positive side, we would say that y goes to positive or negative infinity. In this case, you can see my graph. As the graph gets closer to negative 2 from the right side, my graph goes to, the y values go to negative infinity. And as x goes to h from the negative side. So as my graph moves towards the asymptote this way, okay, you can see my curve and my asymptote up here, my graph is going towards positive infinity. So y could be going towards positive infinity, or it could be going towards negative infinity. So those can be plus or minus. That's the definition of a vertical asymptote. We'll talk about an easy way to find both the horizontal and the vertical asymptotes here. All right? So rational functions can be transformed exactly the same way as other functions. It just depends on how good you are with those functions. When the graphs shift, the vertical and horizontal asymptotes shift with them. Okay? So an example of something in shifted form might be f of x equals, and I'm just going to use 1 over x minus, let's see, x minus 3 plus 4. Okay? So this graph compared to, now again we need to think about the parent function. The parent function for this is f of x equals 1 over x. So in relationship to the parent function, this function would have shifted right 3 and up 4. All right? We're going to talk about it more in terms of how do I know that I'm going to have a vertical asymptote at x equals 3. All right? And we're going to talk about that in terms of the denominator right here. What number do we never ever want to see? We never want to see 0 in the bottom. That means that x can never equal 3 in this function, which implies vertical asymptote. All right? So let's see what we got going on here. Let's do some examples, all right? So if you know your shifts, you can do those very quickly and easily. Okay, the up 4 would shift my horizontal asymptote from y equals 0 to y equals 4. We're going to find some x and y intercepts, and then we're going to find an additional point or two if needed. So here we go. I want to try and graph this using a translation or transformation of the parent function. Well, what's my parent function? Again, I want to keep in mind that my parent function is f of x equals 1 over x. And there's a couple of things I know about f of x equals 1 over x now. I know that it has a vertical asymptote at x equals 0, because I can't plug 0 into there. I know that when we graphed it, we found out that the horizontal asymptote was at y equals 0. Pretty simple on that. I go back and I look at my new function h of x, and I realize that h of x has been shifted 2 to the right and up 1. That means that my vertical asymptote shifts 2 to the right. Where does that put that? It puts the vertical asymptote at x equals 2. My horizontal asymptote has been shifted up 1 unit. So that thing moves to y equals 1. Now, the other way to look at the vertical asymptote is to take your denominator and figure out what makes my denominator equal to 0. Okay? Well, obviously if I plug in 2, I get 0. So there you got it. That's your vertical asymptote. But we can always take that denominator, we can set it equal to 0. If we add 2 to both sides, we get x equals 2, and this is the vertical asymptote. This is also the restriction on our domain. So if I were to ask for the domain of this function right now, the domain is x in the set of reals, but x cannot equal 2. Okay, so we've talked about those earlier in this class. So let's start off by graphing our vertical asymptote and our horizontal asymptote. So we're going to go to x equals 2, and we're going to draw this dotted line just like this. We're going to go to y equals 1. We're going to draw our dotted line this way. All right, and then we're going to find some x and y intercepts and see where we land on this graph. All right, here we go. X-intercept. X-intercept means plug in 0 for y, solve for x. So here we go. Plug in 0 for y equals 1 over x minus 2 plus 1. I need to solve for x. Before I can do anything, well, there's a couple of different things I could do, but I'm going to go ahead and subtract 1 to both sides. And there's a reason I'm doing that. Negative 1 equals 1 over x minus 2. Because now that I have this written like this, I can put a 1 under here, and I can cross multiply this guy. So 1 times 1 is going to give me 1. Negative 1 times x minus 2 is going to be negative x. Negative 1 times x is negative x. Negative 1 times negative 2 is positive 2. And now all I got to do is finish solving. So I'll subtract 2 on both sides. I get negative 1 equals negative x. I divide out the negative 1 from the x here. Negative 1 divided by negative 1 is 1. So I have an x-intercept at x equals 1, or 1 comma 0. There's a point on my graph that I can now use to graph this. Okay? A y-intercept. Plug in 0 for x. One of the easiest points to find. H of 0 equals 1 divided by 0 minus 2 plus 1. h of 0 equals, well, this is going to be 0 minus 2, which is negative 2, so that's going to be negative 1/2 plus 1. So that's going to equal positive 1/2. So I have a y-intercept at 0, 1/2. All right? Now, if I know what this graph looks like, if I understand what the parent function looks like, and that the parent function looks like this, then I know that this graph is going to have a curve right down here on the lower left, just like that. And I'm supposed to have a curve on the upper right. Maybe I don't know where the points go on the upper right though. So one of the things I can do is create a little t-table, x and y. And I only need a couple of points, so I'm going to go to my asymptote. I know that at x equals 2 I'm undefined, so I'm going to go out to 3 and 4. And I'm going to plug those into my function. Here we go. This is going to be 1 over 4 this is 3 minus 2 plus 1. Well, 3 minus 2 is 1, 1 over 1 is 1, and 1 plus 1 is 2. So this whole thing equals 2. I do the same thing with 4. 1 over 4 minus 2 plus 1. Well, 4 minus 2 is 2, so that's a half, and a half plus 1 is 1.5. Let's plot those. 3, 2, 4, 1.5. And voila, there is my graph. All right? What else we got here? Okay, looks like we're on to homework here. So, we'll leave it at that for today.